Today I'm going to just discuss about reconfigurable photonic integrated circuits, the design and challenge. Okay, basically we are started working on reconfigurable photonic integrated circuits. So what are the challenges and what are the design factors we are adapting and we are facing? So those things I'm going to discuss today, because photonic integrated circuit is going to be the future of communication, especially students of communication and the people who are doing research, or people who are planning to do research can enter into photonic integrated circuits, because it has wide opening and a lot of business scope, right? And this is our center for nonlinear science and engineering. In this center there are three groups. Basically I'm working in nonlinear optics groups, and the other group is nonlinear system and nonlinear magnetic material. In the nonlinear optics group, there are two big divisions. One is nonlinear optical materials, nonlinear fiber optics. So I'm working in nonlinear optical material division, and there is another group. People are working in nonlinear fiber optics and nonlinear systems. Basically, this is one of the biggest group, and even they have a paper in Nature. One of very very important group in our sense, right? So here people are working in nonlinearity in many aspects, right? And nonlinear magnetic materials, the other group is nonlinear magnetic material. Here people are working in spintronics and magnonics, right? So this is the small intro about our group, right? So before going into the topic photonics, I wish to introduce my lab. So what I'm really working. Uh, so the work what I'm doing here in Sastra is developing broadband nonlinear optical devices. I hope you all listened to yesterday's talk. In yesterday's talk, Dr. Saini discussed the broadband sources from fiber. Here we are developing broadband sources from periodically poled lithium niobate. So lithium niobate is a crystal, and we are periodically polling it, and we are using this device for broadband, as well as we are working on uh, developing simultaneous red, green, blue laser sources. So compact laser system we are developing. So this is a funded project. And recently we are started working on reconfigurable photonic devices. In the reconfigurable photonic devices, basically our target is to develop a photonic field programmable gated array. So you all know, especially the EC students and EC people who are working in communication, we all very know field programmable gated array. But this is photonic field programmable gated array. So this is our target in this work, right? And optics, optics is one of old topic, and we all know this deals with the generation, propagation, and the detection of light. There are three major developments in optics which made the field optics into different category, different subfields. Okay, the main invention is invention of
Hello, sir. Hello. Hello.
started studying on light material, that is right, the recent optics and we studies quantum optics. And in the case of photonics, there are some you can see here electro optics plays some role, right? Say for example, electro-optic modulator. So electro-optic modulator, which is designed with a lithium niobate crystal, and the electric field is, and optoelectronics. So in the case of optoelectronics, the the basic devices are the semiconductor devices. So let's take a photo detector. The photo detector, it's a semiconductor device, but it works in optics, right? And liquid crystal display. And quantum electronics, in the case of quantum electronics, it's a study about the light and matter interaction, right? And quantum optics, I told you that it's the recent one. Here we study the quantum and the coherence property of light and the lightweight technology. So in the case of lightweight technology, this is the complete communication system. The complete communication system, the electromagnetic spectrum. So in the case why we are working or why we are moving towards optical communication is because of the frequency, right? So here in the optical regime, so we can work in terahertz. In the radio spectrum, this is in megahertz. Okay, so need more bandwidth. So there is no other option. We have to work in optical frequency, right? So especially we are working in infrared. And for long haul communication, we are not working. So less than this ultraviolet and X-ray, they are harmful. So here the bandwidth is more, but it's harmful. So we cannot work in this region, right? And what is the need to study photonics? So this is the question everyone should know, right? So now we have a mobile phone. In the mobile phone,
Hello,
we
sir.
use data. So here there is the data usage through mobile phone. India, in India, 2007. Yeah. Yes. Hello.
Yes, sir. Your voice is getting disturbed, sir. There is some network
Disturb.
issues, I think so, sir. Bandwidth delays, I think so, sir. Hello.
Sure. 1 minute. 1 minute. Yeah.
Yes, sir.
So your voice. 1 minute. 1 minute. I'll. Okay. Say, am I audible now?
Yes, sir. Audible, sir.
Okay.
Okay,
Yeah.
sir.
So so this is the data tariff from the smartphones. Okay, so in India, 2017, the average use of data is about 3 GB per month, right? So if you consider the average use of data is going to be almost 18 or 17 GB per month, right? So 2017, so we were using only uh, 3 GB, roughly 3 GB per month. So in 2000 month. So this is going to increase the data rate, which is going to increase. So 3 to 6 times it is going to increase in 6 years. That we can use the gigabit rates. Okay, the data centers, they need teraflops, right? So so there is a force for the mobile in the future computer. Okay, so whatever the mobile phone we have in our hand is a computer, right? So the future, maybe after few years, everyone is going to have. It is very bulky and it's cost crores and crores, right? So this is one of a supercomputer, the quantum computer developed by Google. Okay, so this is available in so why photonic integrated circuits? Okay, so especially for data centers, right? So in another few years, the amount of double. Okay, maybe in few years, the data traffic is going to be double, right? So with the available electronic integrated circuits, so this data traffic cannot be handled. right? So in this and the other issue, if you go for photonic integrated circuit, you can drastically reduce the power consumption by power consumption. Say, for example, in US, so these three players, they okay, so this 500 megawatt is enough for powering New York City for complete consuming 500 megawatt per year. So this power is enough to uh, 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 power near the complete New York City for 2 years. Right? It's also power consumption, right? And another thing is leader, right? So in the case of leader, normally we use
Hello, sir.
moving parts. So you know, so
Hello. Hello.
so this is and photonic waveguide. So for the reason for discussing photonic waveguide is the waveguides are the basic interconnection element. Okay, so like wires in waveguide. So there are passive waveguides. So passive waveguides are like branches, tappers, and couplers.
Hello.
3 dB couplers. There are Y branch Y couplers, tappers. Okay,
Yes, sir.
so passive waveguide components. So passive waveguide components like the branches, tappers, and couplers, right? And the another waveguide element is light controlling element. So in the case of light controlling element, we can have modulator, switches, polarizer, and other components. Okay, and these light controlling element, they are working in the principle of thermo-optic effect, electro-optic effect, acousto-optic effect, uh, magneto-optic effect, and the nonlinear optical effect. So these effects are very important to control the effect. Okay, so compared to all other effects, so here the electro-optic effect, this EO is widely used because electro-optic effect is very fast, and we can go for even gigahertz speed, right? And the thermo-optic effect, the switching speed is very slow because you have to change the temperature, right? Say for example, if you want to change the temperature of 2 degree, you have to wait for some time. So then only the refractive index of the medium will change, right? So this is the Maxenter modulator. Okay, so can you please go to next?
Yes, sir.
Yeah. So this is the electro-optic modulator in lithium niobate on insulator. LNOI is lithium niobate on insulator, right? So here the input is La and the output is LO, and there are two electrodes, right? The black color is electrode. So here the input is launched, and this is the Y branch. So here the light will be splitted into two. When we apply electric field in both arms, what will happen? The refractive index of the waveguide which is going to change. When there is a change in refractive index, then this will automatically create the phase between the first term and the second term. So if there is a phase difference between first and the second term, then there will be interference effect. So this interference effect will create uh, destructive as well as in constructive way. Okay, if the output LO is the interference is constructive, then you will have the output. Okay, the figure A. In the case of figure A, so whatever the input you send, output you get. Okay, so here this is on state. Input you are sending, output you are getting, and this is the off state. In the case of off state, you are sending the input, but the output is not received. Right. So this is the Mach-Zehnder electro-optic modulator. Okay, then 14. Then so to do this kind of modulator and other components, there are some integration, right? So the photonic integrated circuit, which is not only having the photonic component, which should have some electronic component, right? So the complete integration between electronic and the photonic component is the complete platform. So this can be done either in monolithic and hybrid integration type. In the case of monolithic integration, the entire component are placed in a same silicon substrate, right? And here the main advantage is which leads to lower power consumption and compact size and lower cost, because this specific monolithic integration which use the same substrate, right? And the main advantage of this integration is it's a CMOS compatible, right? So with the CMOS compatible circuits, we can go the data traffic of up to 50 Gbps, right? So now the bipolar CMOS is implemented. Now even more than 50 Gbps we can go, right? Next. And hybrid integration. So in the previous case, monolithic integration, the integration was done in a single silicon chip. But here, this is not a single material. So there are a different material we are going to use. Okay. In the hybrid integration, we can have many components like light sources, electronic control, active and passive photonic components, and light detector. Okay. So here in general, the practically useful material is indium phosphide, right? So this is one simple example of hybrid integration. So in this case, this is lithium niobate on insulator platform. So in the case of lithium niobate on insulator platform, so this number 1 and 2 is a periodically poled lithium niobate structure, and you have directional couplers, right? And so this periodically poled lithium niobate structure, which gives the wavelength of 1550 nanometer, and there is a local oscillator. This LO1 and LO2 is a local oscillator, which also gives 1550 nanometer. And here you can have in this 1 and 2, this pump, you can have some other wavelength also. So depending on the directional coupler, so you can have a logical operation from this. So in the first part, you can have a generation. In the second part, you can have manipulation. In the third part, you can have detection. So the complete communication system can be integrated in a single chip. Okay, so this is hybrid integration because the material here we are using are different. Okay, yeah, next. Right. So and different PIC platform. So as I told, different hybrid and monolithic, and different materials we are using, especially silicon, indium phosphate, silicon nitride, polymer, glass, and lithium niobate, and silica. So each and every material which is having some advantages and disadvantages. So we are going to see those advantages and disadvantages. So and here I'm giving the application and example of the products and the types of wavelength and different PIC platform, right? So if you take silicon photonics, okay, so silicon photonics, so silicon is a monolithic platform, so which will work in almost all the applications, right? Either you consider long haul telecommunication or data center, 5G, automatic sensor, and medical. So almost all the platforms, so silicon will work. And indium phosphide, the usability is limited, and the silicon nitride, and polymer. Okay, there are some polymers which can be used for long haul communication, right? And glass, so glass material can also be used in PIC and the silica lithium niobate, right? So these are all the different material in different applications. Okay, next. Right. Now we see the inside of a transceiver. So inside of a transceiver, you have a receiver and a transmitter, right? So in the case of transmitter unit, there is a laser. Okay, so the laser which is developed built in indium phosphide and the Mach-Zehnder driver. So Mach-Zehnder driver, which is designed with the silicon, and the modulator. So modulator, which is designed with the lithium niobate, silicon, and even the polymer can be used. And to connect one device with other, say for example, source with Mach-Zehnder modulator. So we are using couplers and isolator and lens system. So in the case of receiver side, we need a photodiode. So photodiode can be designed with the indium phosphide germanium, and the amplifier and the coupler, isolator, and lenses. So this is the complete system. So with this transceiver, so the basic light routing. So by basic light routing is, so here we are doing waveguiding, mux and demux, and light coupling, right? Okay, please next. Okay, and the pros and cons of different platform. So indium phosphide and the silicon photonic, silicon nitride. Okay, so these are all different platform. Okay, so this plus is fair, and this plus plus is good, and triple plus is very good, and 4 plus is excellent, right? Okay, now let's take indium phosphide. So indium phosphide is if you use passive component, so this is some uh, good operation. So you can get good operation from the indium phosphide. And so indium phosphide, we can work in almost all applications. We can use indium phosphide. So the pros are best for laser and active integration. So indium phosphide is the material we can have very good lasing. But the problem with the indium phosphide is especially the large scale integration. So indium phosphide is the availability is very less, and here the large volume production is very expensive, and it is almost impossible. And the wavelength of operation is 1.3 to 1.7 micrometer. Okay, so beyond that you cannot go. And silicon, the silicon almost all you can go, but silicon cannot be used for light emission because it's a indirect band gap semiconductor. So here silicon can also be used by hybriding. Okay, so by having some other layers, so you can have silicon lasing, right? So it is hybrid. So hybrid is different layers, different layers. So silicon is the platform. With the platform, there are different many layers. So with that layer, we can generate the operation. For example, lasing operation and optical amplification and silicon nitride, and especially lithium niobate. So in the case of lithium niobate, so lithium niobate, the pure lithium niobate can be used in modulator. Okay, so compared to all other material, so lithium niobate modulators are being currently used and commercially available in day-to-day communication. We are using lithium niobate modulators. Okay, and other, so passive component, it is hybrid silicon on lithium niobate on insulator, and there are some other platforms we are using. Okay, here this is very good material for modulation of light. And the con in lithium niobate is low damage threshold. Compared to other material, the damage threshold is very less. And industry status, so lithium niobate is commercially available and high volume, so mass production people are doing, right? And in the case of indium phosphide, this is ramping up. Okay, and silicon photonics, so the production is very high. Okay, high volume production is available even today. The material which you use, silicon photonic integrated circuits, are very high. Okay, next. Okay, now we'll see the detailed advantages and disadvantages. Okay, in the case of three-phase material, so with the three-phase material, so these three-phase materials are a very good material for lasing. So with the broad spectrum, you can cover. So you can cover the wavelength range from 0.5 to almost 3 micrometer. So 0.5 micrometer to 3 material, 3 micrometer. And there are plenty of advantages when we use 3-5 platform. So the 3-5 platform can be used as a laser source, amplifier, modulator, detector, and a monolithic. So it can be used the monolithic passive as well as active components, and the high-speed electro-optic characteristics you can get it, right? And the highly reliable material. So this is the main disadvantage is CMOS integration, right? Silicon can be easily integrated CMOS compatible, but this indium phosphide is not CMOS compatible. And another problem here is the propagation loss. The propagation loss here is greater than 0.5 dB per centimeter, right? And the mass production and low index contrast. So index contrast is very important because we are going to make a waveguide structure. So we all know for a waveguide, you need a core and a cladding. So the core and cladding refractive index difference should be slightly large. Okay, if the index difference is very less, or the if the material or if the platform which is having low index contrast, then guiding will be poor, right? Okay, next. And silicon photonics. In the case of silicon photonics, uh, silicon can be used almost everywhere. Okay, uh, so data centers and optical communication, optical interconnects, and it can be used. Okay, and it can be used as a modulator, detector, source, and the main advantage, this is fully compatible with the CMOS, right? Because we need to integrate electronics and photonics. So CMOS compatibility is very, very important, right? And so this has the ability to reuse the huge technology base and the supply chain from electronic industry. Okay, because already we are using semiconducting. So here the silicon can be easily compatible with the other semiconducting devices, right? Okay, next. Uh, the advantage here is low cost and CMOS compatible and high index contrast and transparent in 1.3 to 1.6 micrometer region. And with this silicon, you can go with the sub-wavelength dimensions. Okay, and main disadvantages: indirect band gap and weak electro-optic effect. Okay, so here electro-optic modulator cannot be done with the silicon, and lossy. And another important, so you cannot make light emission, right? Because it is indirect band gap semiconductor, right? Next. Okay, and glass. Uh, so in the case of glass, silica on silicon. Okay, so the base platform is silicon. So on silicons, we are going to use glass, right? So here the main advantage here is, so different dopant can be used, because in optical fiber we use glass fibers. So you can make different dopant. Okay, you can dope different materials to change the refractive index, right? So different dopant can be used to create huge index contrast, right? And another main advantage here is uh, the core material here we are using is silica, and this can be easily coupled with the fiber. So that is one of the main advantage of uh, glass platform, right? Go to next. Right. So the advantage, so the low propagation loss, the propagation loss, is 0.01. So compared to the indium phosphide, the propagation loss of glass is very, very less, and low polarization dependence and broad wavelength coverage. Okay, so in the case of silicon, you can cover the wavelength of 1.3 to 1.6 micrometer, but in the case of glass, you can cover the wavelength from visible region to IR region. So that's the main advantage of glass. And low coupling loss. So especially if you couple the device with the fiber, so we need to consider the coupling loss, right? So because already here in the medium, we are using glass as a medium, and glass as a fiber medium, right? So the coupling loss, there is a index matching between the PIC and the fiber, right? So the coupling loss is very less. And thermo-optic effect, so this is almost inherent for thermo-optic effect. Okay, so low temperature difference, even if the temperature is changes, the performance of the device which is going to change lightly, right? And there are major disadvantages. So large model area and bending radius, so this is another disadvantage of uh, glass medium. And limited active functionality available, and most remain in lab. Okay, so the you cannot use the glass material for almost all the applications. So the functionalities are limited. And so this fabrication is bit costlier compared to the silicon platform or indium phosphide platform. This uh, silica on silicon platform is bit expensive, right? Okay, next. Yeah, so some applications. So this one, WDM multiplexer, even presently we are using glass, right? And fiber to home, fiber to uh, fiber to the home splitters, we are using glass. And the thermo-optic switches, we are using in glass. And hybrid integration, so this is integrated with the 3-5 semiconducting lithium niobate and as well as polymer. So you can integrate the glass with other platforms, right? Okay, next. And polymer. So polymer, SU8, PMMA, polymethyl methacrylate, and ZPU. So there are different polymers. So those polymers can also be used as a platform for designing integrated photonic integrated circuits, right? So the main type of platform here is, so these polymers can be used to design a passive as well as active component, as well as the electro-optic component, right? Okay, next. So the advantages and disadvantages. So it has very less propagation loss, so less than 0.5 dB per centimeter, and low birefringence, and precise and continuous engineering of material property, and the large thermo-optic and electro-optic and nonlinear. So nonlinear property is another important property uh, in communication. And good and easy ability to process. Polymers are very handy, right? And the main weakness here in polymer is low index contrast, right? As I told you in my previous slide, high index contrast is important here for a waveguide structure, and not suitable for high temperature application. So because these are all the polymers, so you cannot go for high temperature. And some polymer materials raise some reliability issues. Okay, yeah, go to next. Okay, so these are all so till the previous slide we have seen advantages and disadvantages. So now till the previous slide what we have seen, so whether we can generate electronic component, photonic component, and active, passive, and modulators. Okay, so everything in one, right? So if you integrate everything in one, so what you have to face, so you have to study the electronic property as well as the photonic property. So for studying electronic property or studying electronic characteristics, there are plenty of softwares which are available. But studying photonic property, the software which are available are very less. So for example, the electronics and photonic signal can be considered as a analog signals. Okay, so in the case of electronic signals, we can use the spice simulator. So this is an open simulator, right? So with the spice simulator, you can simulate the integrated component and you can study the characteristics, right? And with the spice software, you cannot study the photonic, right? So the characteristics of light. And the main problem with the characteristics of light, so light signals are very speed, right? And so here the frequency is about 200 terahertz, right? So there is no dedicated open software, open source for electronic and photonic simulator, right? So this, if you have a dedicated electronic and photonic simulator, then we can integrate many circuits, or we can design many circuit, or we can study many circuits, photonic integrated circuits. Go to next. And design of photonic component is another big challenge. So in electronics, we have a process design kit. So process design kit is a software. So with this software, you can design, you can study the component, right? So so you have a circuit. In that circuit, each and every component you can design or you can study with the process design PDK kit, right? So similar PDK kit is not available in photonics. So here we have to study the component layer level, component level, and the system level. So for layer level, component level, system level in electronics, there are different software and different groups they are studying, they are working. But in the case of photonics, the case is different. So there is no group for studying layer level, component level, and system level. So a person who is working in photonic integrated circuit, they have to do all the layer level, component level, and system level simulations. Okay, so everything has to be done through a single person. So the workload is very high if you go for photonic integrated circuits. Okay, next. And multiphysical effect. So multiphysical effect here is the temperature effect. So in general, the photonic waveguide elements are significantly affected by the temperature. Hence, outside temperature variation should be compensated by thermal tuner. But the laser driver circuitry and the driver circuit for modulator also induce self-heating. Okay, so this heating which changes the property. Okay, so because I have already told you the thermo-optic effect. Okay, so in the case of thermo-optic effect, then the refractive index of the material changes, then the entire performance which is changing, right? In the case of silicon, this is almost stable, but the problem with the silicon is there is a uh, free carrier density will result change in both refractive index and absorption. Okay, optical absorption it changes as well as the refractive index. Okay, so this is the carrier injection effect, the thermal induced carrier injection effect. Next. And the variability. So variability in the sense, the effective refractive index of waveguide core is strongly dependent on actual geometry of the cross section. Okay, if the cross section, for example, the height and the width changes inside any of the lobe, then there will be a variation. The active refractive index which changes, right? And especially in ring resonator, right? So small width or height variation will induce a significant shift in resonant wavelength. Okay, so this is the best example in variability. Okay, then next. Okay, in routing, so for in routing, so minimum bend radius are recommended, and there should be a enough spacing between the routing waveguides. Okay, so one waveguide to another waveguide, there should be a some minimum spacing. If the spacing is very, very small, then there will be evanescent coupling. So this evanescent coupling, again, it's a very, very dangerous effect in communication, right? So because the signal will move from one waveguide to other waveguide, then there will be a huge crosstalk. And another problem here is the reflection, okay, the back reflection, because one component to other component, if you connect the waveguide, then there will be a back reflection. So that back reflection, right, which is cat S. So that back reflection, again, it is a crosstalk. And another problem, so even this back reflection, which creates interference effect, again, it is very dangerous in peak, right? Okay, next. Yeah. So this is the parasitic effects. So that is the unwanted effect. So parasitic light can interfere constructively as well as destructively, complicating the calculation of the actual net result of the parasitics. Okay, so this parasitic effect, which comes from the back reflection. Okay, so we calculate, so this much light or this much light intensity will come to the output, but the actual output may increase or decrease, right, because of this back reflection, right? And there will be coupling problem. Okay, so this coupling problem will also create the parasitic effects, right? And in addition, so optical nonlinearity. So nonlinearity is another major issue in PIC. So nonlinearity we need in some cases for generating higher harmonics, we need nonlinearity, but for general communication, we don't need nonlinear effects, right? So nonlinear effect will change the input signal into some other wavelength, right? So this is very dangerous effect. Okay, next. And some features of silicon on insulator and lithium niobate on insulator. So especially the silicon on insulator, which is high light confinement and sharp bend radius due to high index contrast, and you can have zero change utilization of CMOS fabrication because this is CMOS compatible. And uh, so the temperature tolerance, okay, the temperature tolerance is bit high compared to other platform. This temperature tolerance is bit high in the case of silicon on insulator platform. And in the case of lithium niobate on insulator platform, so you can have low propagation loss and well confinement because the index contrast between the core and cladding is very high. So you can have very good confinement and good nonlinear behavior. So in the case of silicon or other medium, so you cannot get nonlinear behavior. So if you for example, if you want to have generate higher harmonics, you need nonlinear behavior. So that nonlinear behavior you can get only from lithium niobate based lithium niobate platform, right? Okay, next. And so these are all some results of our work. So we have developed one cross two gated Mach-Zehnder interferometer. So in the case of one cross two gated Mach-Zehnder interferometer, the input is 1 and the output is 2. That is 1 to 2, right? So this is 2 cross 2 interferometer, right? So this is 2 cross 2 model, and we uh, make null of one input, and we are sending only one input, and here we are not using. And there is a cross state as well as bar state. So bar state in the sense, so light A which is going to light C. Okay, so this is bar state and this is the cross state. Okay, so the input light which reaches here. Okay, so now I'm giving a input here and I'm changing the voltage. Okay. So depending on the voltage, I can switch. I can make the light to go to this branch or this branch. Depending on my application, I can switch. Okay. Then similarly here. So here I can create an interference. So these two will create a phase difference between the interacting wave, and here I can get the light or no light, right? So 0 or 1, I can get it. Similarly here I can get 0 or 1. Okay. So now you consider the bar state operation, right? So bar state operation in the sense, so input A will reach input C, right? And transmission. So transmission 0 in the sense, so this is the maximum. So maximum transition we can get it. And in the D port, in the case of bar state, we need output only from the C, right? And in the case of D, it is the transmission is very less, because it is roughly minus 25 dB. Minus 25 dB is almost negligible, right? In the case of cross data, so that is the light which is coming through this port, almost constant, almost constant. And the light which is going through port C, right? Light which is going through port C is very less, right? So the bar state as well as cross state, we can have maximum light, right? Go to next. So this is 2x1 gated Mach-Zehnder interferometer switch. So here 2 inputs and 1 output, right? So you have a bar state and a cross state. So bar state, for example, A to C is the bar state and B to C is the cross state. So the bar state and the cross state. For example, I'm sending inputs, input A. Okay, so that can reach the input C. Even I can send the input B and that will reach input C. So depending on the voltage which I operate, I can switch the input of operation. Okay. Now the bar state as well as cross state, the transmission loss is given, and wavelength what we consider here is 1530 nanometer to 1570 nanometers. Next. Yeah. And this is silicon on insulator. Silicon on insulator. So we have developed a switch. So 1x1 on off switch. And this is cross sectional view. And this is the general view of the 1x1 switch. Right. And in the case of on state, so whatever the input I give here, I'll get the output, right? Now I'm changing the voltage. I'm changing the voltage here. And even if I give the input at the output, I will not get anything, right? So here, the mode coupling mechanism, the light will be shifted. Light will be shifted from this waveguide to this waveguide. So here we have a tapered structure. So light will propagate here, right? So this is on and off switch, because the reason I'm talking about on and off switch is the logic gates like AND gate, OR gate, whatever the gate we use, it's a switch, right? Switch of different mechanisms. Similarly, with on and off switch, we can do all logical operations. So once you do all logical operation, you can go for integrated circuits, right? Next. Right. And this one is the 8x8 dilated Banyan switch we have developed. And here, this is the input port. And this is the 1x2 um, 1x2 switch. And this is again 1x2. And this is 2x2. And this is 2x1. And this is 2x1. So by keeping a 1x2 interferometer and 2x1 interferometer and 2x2 interferometer, you can have a Banyan switch, dilated Banyan switch. So we have studied the transmission loss as well as crosstalk for this complete architecture. Right. Next. And this one is photonic configurable logic block, because logic blocks are the basic building block of FPGA, field programmable gated array. So we have developed a photonic configurable logic block, right? So with the help of 1x1 Mach Zehnder modulator, right? So and here this UPG is the universal photonic gate. So this universal photonic gate, which is designed with the 1x2 or 2x1 modulators, right? And so here you have a CW laser, and whatever the operation you want to perform, you can perform with the configurable logic blocks. Okay, next. Yeah, conclusion, the merit and demerits of various design platform is discussed, and in our lab, due to the better light confinement and CMOS compatibility, so lithium niobate on insulator and silicon on insulator platforms we are largely studying, right? And these platforms can be used for telecommunication network, data center, fiber optic network, and other major players, right? Okay, next. Okay, and these are all the references. Next. Yeah, and acknowledgement. Okay, I acknowledge my supervisor and my postdoc advisor and my research scholars and Sastra University, funding agencies, and organizers of this FDP. Next. Okay, thank you.
So thank you, sir.
Yeah.
Request participants, if you are having any doubts, you can please unmute your mic and you can ask. So participant side, if you are having any doubts, you please unmute your mic and you can ask.
Yeah.
Yes.
Yeah, I'm waiting for some questions, comments.
Yes, please carry on, sir.
Sir, good afternoon, sir.
Yeah, good afternoon.
Sir, is there any tools to implement this one, sir?
Yeah, there are plenty of tools. Okay, there is no open sources. Yeah, there is no open sources. Like normally we use Lumerical and Opti BPM,
Okay.
Opti FTDD. There are different tools, but these tools are not free, so you have to purchase. So that's the problem.
Okay. Okay, sir.
Hello.
Thank you.
Hello.
Yeah.
Good afternoon, sir.
Good afternoon.
Sir, I wanted to know about the Spice software and other software. What is the usage and what are the different kind of uses things?
Spice software is open source.
Okay.
Right, so you can use for designing electronic integrated circuits, right? So that is Spice, and BPM. There is a beam propagation method. Opti BPM software is Opti BPM. So how the beam is propagating in photonics, how the beam is propagating inside the waveguide, and how we can have the logic operations. So those logic operations you can study in Opti BPM, Opti FTDD, and there is another software called Lumerical. Okay, so component wise you can study, but if you go for integration, so there is no complete integration software, so you have to develop, especially in photonics. There is no complete integration software.
Okay, sir. Thank you, sir.
Yeah, thank you.
Is still any more doubts? If you want, you can ask. Please unmute your mic and you can ask.
Sir, if you want to collaborate with based on the topics, any Industry collaboration is there.
Yeah, there are plenty of industrial. Okay, I have deleted plenty of slides, but
Okay.
I thought of giving many industrial views. Right?
Okay.
Maybe I can share the list of companies and who are the major players,
Okay, sir.
right? And even the current business statistics. So everything I have, but I haven't included in this presentation.
Okay, since the tools are not open, so
Yeah,
we must collaborate with this. Otherwise, we can't
yeah, yeah,
give
yeah,
for
yeah,
this.
yeah.
Okay. Thank
Sir,
you.
Thank you.
sir, can you give me some basic research problems for BTech and MTech students in this photonic integrated circuits in optics?
Yeah. So the challenges I have given, right? So I have given only 6 challenges. There are almost 10 challenges, right? So each and every challenge can be given as a project for BTech, MTech, or PhD, right? So if you go through the challenges, what we encounter, that's a project. That's the idea of the next level. Yeah.
Yes, is there any more still doubts? If you are having any doubts, you please unmute your mic and you ask. If there is nothing, we'll conclude the sections.
Uh, okay. First,
So thank
first
sir.
I'm sorry that there was some internet
Yes, sir.
problem in
There
between.
is yes, sir. Some internet
So
problem.
because of that, my flow was slightly stuck. I was
Yes,
in
sir.
a
Yes,
good
sir.
flow, good mood, but due
Yes,
to
sir.
this internet disruption,
Yes,
I
sir.
was not in good flow. So sorry for that.
No
Okay.
problem, sir. Anyhow, the section is on track, sir, with both the
Okay.
conversations from the host and the resource person side. Thank you
Okay.
very much, sir.
Yeah. Thank you. Thank you.
Thank you very much for your wonderful and informative section, sir, where these many
Okay.
research persons can gain these a startup how to find out the problems. I think they have
Yeah.
understood how to find out a problem using these challenges. Yes, sir.
Yeah. Okay. Thank
Thank you
you.
very much, sir.
Yeah.
So, on behalf of Rice Krishna Sai Prakasam group of institutions, I thank you very much, sir, for giving your wonderful sections and
Yeah.
very informative sections.
Yeah. Thank you all.
Thank you, sir. Thank you.